Let me just read it. It's what is the average rate of change of h of x equals 2 to the power x plus 1 over the interval 2, 4. Yeah, the plus ones on the power too.
Is it up here?
Yeah.
Okay. So what are we thinking?
Uh, the the difference quotient, which is like the slope equation, because it's asking for the rate
We're
of
going
change.
to look at it like slope.
Yeah, because that's what I thought when it's the rate of change, right? Because like slope.
Big fan, right? That was excellent. Saw something, knew that resonated with something that is more meaningful to you. Great. Let's get a picture, just because pictures are always a nice thing to help add intuition, right?
Hmm.
This is an exponential graph that's shifted a little bit, but like I don't really care. It's going to be something like this, right?
Yeah.
And then I'm looking across 2 to 4. So here's 2, here's 4. I could figure out heights even if I wanted to make this picture nice and accurate. Plug in 2, that'd be 2 to the third is 8. So this is the height right here of 8. And then I plug in 4, that's going to be 2 to the 5th. 2 to the 5th is going to be 16, 32. I think it's 32. And we're looking for the average rate of change. You very nicely stated that rate of change is slope.
Is this gonna be
But
like the secant
specifically
line?
here, the rate of change is across 2 points versus a derivative, which a derivative would be if I was looking at the slope at a moment, and I have 2 here. So that's where the average comes in, is the average is talking about the slope across 2 points.
Mm-hmm.
Okay, so I got across 2 points. I want to find the slope. How do we do that?
I was thinking like you connect the secant line from the 2 points. Is that something?
We can draw it with a secant line. That's fine. We can put that in there so that now we're looking at the slope of the secant line is the same slope as what I would get for my average rate of change. We've got an even better picture. Okay, good. How do I do this?
Just plug the thing into the slope equation, right?
Good. Slope equation is
y2 minus y1 over x2 minus x1.
okay. Good.
And then so it would be 4, no wait. It would be 32 minus
Good.
8.
Yep, which we got from 2 to the 4 plus 1.
Yeah.
Good. Minus
2 to the 4 oh wait. 2 to the 2 plus 1.
2 plus 1. Good. Divided by
2 and 4, or 4 minus 2.
4 minus 2. All right, and that comes out to, like we said, 32 minus 8 over 4 minus 2, right?
Oh yeah.
Good. What's that get us?
32 minus 8. Oh shit. 12.
12. So the average rate of change is saying that I'm changing at 12 units per sideways step, right? 12 rise for every 1 run on average. Let's double check that with our picture. Does it make sense that if I go up 12 and I go across 1, I would be at 20, right?
Mm-hmm.
And then I go up another 12 and I go across another 1, I would be at 32 and 4. Yeah, that's great.
Damn. I don't know why I didn't think of just putting the 2 into the x. Yeah.
So it's not always about like what do we have to do, right? It's always a matter of if you hit a roadblock. Most of the mathematical mindset that we're trying to develop in any math class is not, do I know how to solve this problem? We're not trying to hit this like alchemy. Alchemy is like, I know what to do, I follow the recipe, magic happens, I get gold out of lead. We're trying to instead just develop a mindset of like, if it doesn't work, what else can I do? right? How can I double check it? How can I make it intuitive? So think about it less about trying to like go through a forest with a map, and think about it more like you're going to run into the forest, understanding that you're going to hit trees head first and just be very okay with bouncing off them and pivoting, right? Like that's what we're doing, is we're just like smashing our way through the forest, not by trying to bust through trees, but just by bouncing and course correcting.
I think that also the thing that threw me off was like the X plus one being in the power up there. I was like, how am I gonna
You worked with those,
get that down? Yeah.
so
I think
don't let
also
these be
like drawing a
intimidating.
graph.
If it is, just find another method that's logical and pivot to that.
Yeah. Okay.
Excellent,
So
good stuff.
drawing a graph would also be like a good way, like in the test, just like explain your thinking too, right?
I love it, right? If you look at the course rubric is designed where I'm just trying to understand if you understand. And if you're like, I understand some of it, but not all of it, that's already like a 50 or 60% credit I can give you. Like what I'm really trying to break the habit of is when students in the course are just doing things because they saw me do it. It's like that doesn't, like, you don't even know why it works. You're just doing things because you saw symbols before, and it's very obvious to me as a grader because I have lots of experience like working with students and tutoring them. I know why you are probably writing what you're writing on the paper. So like if I see somebody who's just like dividing by like a thing because they saw me do it, like they're putting a 1 over square root type thing into a problem that has nothing to do with square roots, I know they're just doing it because they saw a problem like that in the past. Versus if they were like, here's what I know the question is asking, here's what I tried, here's a picture that goes along with it, but I didn't know what to do past that, I can credit that at like 60%. But if somebody just smashes symbols on paper and gets the correct answer through a horribly wrong approach, even if the answer is correct, they get a 0. Because I don't care that their answer is correct. No one in the real world will trust them. And I definitely think that you can do more damage running out into the real world, broadcasting something as true that you don't understand versus just saying, I'm not quite sure, but here's what I do know, right? A little bit of truth is always much, much better than a whole lot of wrong. All right, anyways, here we are. All right, so we're trying to estimate f prime of 3. So again, we've got f prime of 3 meaning what?
Speed of
We can think of it as speed. I'm okay with speed. Speed if f means what?
F. The curve. Or
The curve, yep. So if f prime of x is speed, then f of x means what?
position.
There you go. Nice. So it's fine. Any of these metaphors, any of these models of logic are completely fine. We just, if we're going to adopt it, then we've got to make that permeate the entire situation. So if right now this says that I have a position graph, because it says that I have graphed my position, my f of x, it's asking me about my speed. My speed when?
At time 3.
Very
That's
good. So we can
seconds.
say f prime of 3 means the speed at 3 at like x equals 3, right?
Yeah.
Good. Okay, so I can kind of look over here and I can say, well, what's happening to the position? It looks like it was very far away. It looks like it cranked on down to being close to 0 distance away. So it went from high distance away to low distance away. That means that the speed should be what?
Decreasing.
I don't know about decreasing, but it's definitely a speed that's bringing me closer, right?
Yeah.
And it's bringing me closer from far away, so that would mean it's a negative speed, right?
Okay. Yeah.
See, decreasing speed means that there's like, I've got to think about the speed at one point versus the speed at another point. And I really like, we could do that, but really it's just saying, all right, I'm coming in towards the negative because I was very far away positive and now I'm less positive. That means I have changed negatively. Okay, maybe that's a tough story for us to use. We could also draw it. What's speed going to look like in this drawing?
Um. Just a dot, right? Or
Dot would be a moment, and it'd be a moment with position, right? Because it's a graph of position.
yeah.
Speed would be how I'm changing that position. So how do we graph change? How does graph a change appear?
The slope.
Slope on the at that moment, right? Slope of the tangent line.
Yeah.
So that's our tangent line right there. The slope of that tangent line means like at that moment it was kind of heading in this direction, or conversely kind of came from that direction ish. So we're trying to look at the slope of that tangent line as a way of figuring out the magnitude of speed. So it's moving towards the negative. It's moving towards the negative, not as much as it used to be. What's a good estimate for that? How would we estimate, using this picture, the speed?
Kind of just like picking two. I don't know. Kind of finding 2 points on that secant or that tangent line, maybe, and then
Yeah, we might as well, right? I mean, it is saying estimate, so this is not going to be exact. There's no way for us to make it exact. My drawings probably aren't the best, so maybe I should use the line drawing tool to help make this a little bit cleaner. Something like that, right? Okay, so let's grab some points. What points look good?
x6 and
Six
x0.
with a y value of
Are we 0?
good. So I've got 6 comma 0. We'll use that one. That looks decent. And
then x equals 0. 0, 2.
we could, but then I've got to have 2 different points, both of which are kind of guesses, right?
So use the position 3.
Yeah, let's use this one. This one, at least I know this one's true because it's given it to me in the picture. So that would be 3 comma 1, right?
Yeah.
So we're gonna definitely use our artistic skills, but we don't have to like go overboard on using them for all the data. We might as well use the good data if it's provided. So what would the slope be?
Just 0 or 1 minus 0, and then 3 minus
So we're doing
6.
the y2 minus y1 over x2 minus x1.
Yeah.
So you get 1 minus 0 over
3 minus 6.
3 minus 6 gets us
Negative 1/3.
negative 1/3. And again, that looks like it matches with the picture. Should be a negative slope, pretty small, shallow.
Yeah.
Should be
Yeah.
good.
Yeah.
Did that work on your end?
Yeah. Yeah. It made me like.
Great.
Yeah.
Excellent. Good stuff.